Okay, I'm gonna start the recording. I'm just paranoid this thing is not gonna record. Okay, I think everything's all good. All right, everyone see that? I think in the top right corner there, I prepared these notes last year and I'm just readapting them this year. I'm pretty sure in the top right corner there, if you scan that, it brings you to my notes. And so if I ever go too quick or whatever and you need to go back to anything, that's a good QR code to have on hand. I guess a bit about myself. I'm like a graduate structural engineer, so I'm in like my first year of like out of uni, like working and stuff like that. Is there anything else to say about that? Not really. Yeah, so I can provide a little bit more like stories, anecdotes. Yeah, I can provide some anecdotes from work and stuff like that related to concrete design, which might be useful. So if you've got any questions, chuck your hand up. It's always good to ask. Yeah, so a bit about the course before we do anything like technical, I guess. Oh, also, I just want to say it's good to see some familiar faces, and also a couple of you I don't think I've seen before, maybe. But like, yeah, welcome. I'm Henry. I don't think I said my name. But give you some context about the course, what to expect. I guess the great thing about this course and about Taiwan, there's pros and cons, right? Great guy. I'm not going to talk shit about Taiwan, but like pros and cons. Pros, it's pretty consistent every year, right? What you see like last year, what you see the year before in the final exam, you can pretty much expect to see. Like he's not going to throw like some random curveball at you, so that's good. And we have some like solved like past papers, all in that folder, by the way. So if you ever need to like after this go and look at the past papers, see my working out for it in the top right. So yeah, the course is like pretty consistent. I guess cons is I want to say it's like I don't want to scare you, but like I think it's pretty hard. Like this finals, I think it's worth 60% maybe. Hurdles like 40%, right, Janice? What's up? Yeah, so you kind of want to be able to get over that like finish line. In terms of how the finals is constructed, maybe I'll start doing stuff. Yeah, 6 questions generally. So the first 3 questions are material science related, all to do with cement. I know a little bit about that, but I haven't like touched the chemistry like for it in a while. And to be honest, most of the time it's pretty close to what you'd see in the workshops anyway. So if you like practice those kind of workshop material science questions, you'll be right in my opinion. Yeah, that's not really my specialty. It's not really what I'm good at teaching. So you can try to ask me questions about it. I can try my best to answer it, but I'm going to stick more to like the solid mechanics, engineering mechanics side of things, which is like the second half of the exam and the part that's worth more. So as you can see here, kind of how I laid it out is like the cement part's only worth 20% of your actual exam mark, even though it's 3 questions. So you can expect like kind of shorter questions related to that. Questions 4 to 6, that's worth 80%, right? So that's a bigger chunk. In the past, there's sometimes only been 2 questions, as in like say like question 4 and 5, rather than 4, 5, 6. But then it just ends up being like those are bigger questions. They have more parts to them. So yeah, it'll be something in this ballpark. Yeah. So the topics that you can expect to see in the finals is flexure, right? Which is this course is week 4 and 5. You can expect to see shear, which is week 7, I believe. Serviceability, week 8. And columns, which was week 10, probably like the most recent topic. And then like there was also probably like a little segue or like a little tangent into one-way slabs. One-way slabs are kind of like beams, but a little bit different. And so a lot of the design of one-way slabs is just a variation of flexural design, if that makes sense. Yeah, so right off the bat, in terms of what you are expecting to see in the exam, do you guys have any questions? Anything like that? Or is that like pretty clear? Yeah, cool. Seeing some nods. Great. I see some people scribbling stuff down, so I'm going to leave that there. But I'm going to start talking about stuff here at the bottom, right? So I like to start as general as possible. If I get too technical with my language here, just stop me and be like, can you explain that again? Or like, can you like simplify that, or like ask something, right? But what I'm trying to do is I'm trying to break down the concepts that you need to do flexural design. So in my opinion, flexural design is like the main takeaway from this course, right? When you're designing a concrete, so this is like concrete structures, like this is the course, right? The main takeaway from this course is they want you to be able to design a concrete beam, basically, right? And to design a concrete beam, you need to be able to do the flexural analysis, and then you need to be able to do the shear analysis as well. And serviceability. Those are kind of the three main things, but the first one that they're going to teach you, the main one that's like highly likely, hi Tracy, is highly likely to be in the exam is flexural design, okay? Some variation of flexural design. So I want to run over the skills required to do it, because low-key, it's the hardest topic, right? Flexural design, it's like a huge hurdle for a lot of students, and if you never really overcome it, then you can't really pass the course, I guess. Right, Janice? Yeah. So, no, so like shear design, there's like some other topics that you can kind of get away with. Yeah, you can kind of get away with like half knowing it and following steps and getting through. That's fine. Yeah, flexural, I really want to like touch on properly. So, the first dot point I've got here for flexural designs, like the skills required. Find the shear force diagram, find the bending moment diagrams. So I think this one's the most intuitive, because I guess you've been doing it since like 1300, it's a prerequisite of this course, right? Now there's only one thing that's like a little bit different from 1300. Two things, okay? First thing is load combinations, right? So I want to say, okay, chuck your hand up if you've done steels before. Okay, so like most of this class, right? So steels, they run you through load combinations pretty thoroughly in the first week, and then you just keep going. For concrete, like they kind of expect you to know what load combos are already, and they kind of just, yeah. But like if you haven't done steels, you might not know like load combos properly. They will also make more sense when we run through examples, but in general for concrete, the only ones that we really care about for strength design, how am I going to do this generally? R star. So if I say R star, that could mean M star, it could mean V star, right? R star is like a factored load, right? Factored. So there's two load combinations for strength. 1.35 G and 1.2 G plus 1.5 Q, right? So if you've gotten to this point in the course, hopefully you know what that means, right? But otherwise you're gonna need a cram. So G, dead loads, right? And then Q, live loads. So just breaking that down a little bit further, G you can classify into self-weight and superimposed dead loads. Q is just live loads. You don't really need to break that down any further. Just like a little bit of context. So self-weight is like the weight of the element itself, right? So if you have a concrete beam, right, you can imagine it's pretty heavy and needs to be able to support its own self-weight. SDL is anything that you put on top of it. So for example, we might be on like some kind of concrete slab right now, right? Superimposed dead loads might be, let's imagine there was like a partition wall that divided the room in half, and then that's not planned to move. That's a dead load because it's going to be there for like 100 years or something like that. So that's something added on top of the actual element itself, and you're not planning to move it, right? Live loads are like humans, right? Or like bikes or like cars or anything that is essentially going to be there one day and maybe not the next, right? So more on and off kind of loading. So basically in AS1170.0, we spell out these load combinations, and there's two that we have to check for. One that's like dead load governed, which is the top one, and one which is like live and dead load governed together. And that one has like a big exaggeration factor for live loads, 1.5, right? What it's saying for that 1.5 part, I just want to explain, is we're going to pretend the live loads are 50% worse than they actually are, right? I'll just give you a random example. So say you're in the elevator in like the civil building or something like that, right? That's designed for, I don't know, like 10 people. But one day, like you decide to fit in like 20 people in the elevator. That's like why we have to have these exaggeration factors. there might be more people than expected on like a typical service live load on any given day. So that's the exaggeration factor we design for when we're designing for strength. Strength design is also called ultimate design. It's also called safety design. It's just the absolute maximum load, right? So that's kind of where we're going with flexural design. Yeah, does anyone have any questions about load combinations? Because what we do is we're going to exaggerate all the loads, all the dead loads, all the live loads, and then combine them, add them up, and then we use those kind of loads to figure out our bending moment diagram. We're going to use that to figure out our shear force diagram. I've drawn like mini versions of them here. But basically, for example, in like a simply supported beam, the biggest bending moment is going to be in the middle of the beam, right? And so that's the section that's going to fail first. Like that's where you'd expect the cracking to occur first, assuming it's like distributed load, right? And so that section, right, of the concrete beam is the section that we're going to design for, because it's the worst case loading, right? For shear design, which we'll talk about a bit more later, the worst loading is actually at the supports over here, because at the supports is where the shear is the highest, okay? Now there's a little bit of a caveat to that, where we have something in the code which talks about positioning where we consider the maximum shear, 1 DO, which is the depth from, I'm rambling, but like it's a little bit away from the support, right? It's a little bit away from the support. I'll explain that a bit more later, potentially when we talk about shear. But does that all make sense? So that's just finding the external loading happening on the building. It has nothing to do with concrete itself. You apply the same principles pretty much for steel, for timber. Yeah, it's just for a structural element. Okay, all good? Yeah. All right, here's where students lose the plot generally. Strain. So in most courses, steel's included, you can kind of get away with not knowing what strain is. Well, too bad, because in this course, you need to know what strain is in order to do flexural design. Strain is probably like the hardest concept. It's like the second concept that you talk about in solid mechanics, and then you kind of just move on. But yeah, like flexural strain is probably the most important takeaway from this topic in the course, and like it's how it's applied in real life. So the idea, right? Oops. Haven't really given myself much space. I'm gonna make a new page. So just very quickly, engineer's beam theory, right? The idea is if I have like a simply supported concrete beam, and then we have our uniformly distributed loads acting down on it like this, right? It's going to cause the beam to bend, right? As you can kind of see, just like also intuitively. The idea is that one side of this beam we say is in tension and one is in compression, right? Someone want to have a stab at which side's which?
Bottom's tension.
Bottom's in tension. Very good, Andy. So basically, if you think about the middle of the beam, and if I measured this with protractor or whatever it's called, right? That's L, right? LO, the original length of the beam before it was bent, right? At the bottom, we're going to have LO plus some kind of extension, delta L, right? So that extension, like once we stretch the beam, that's now in tension. The beam's being pulled apart at the bottom, right? At the top, right, we have that original length, and then we subtract delta L. So that's now in compression, because it's actually shorter than that original length was, right? Does everyone kind of agree? So that's like tension, that's compression, that's the idea. So when you have like flexural beam theory, it's just saying one side's in tension, one side's in compression. Now how we visualize this on a graph, right? Because we could choose to try to map this against the depth, like up and down, right? We map it with strain. So basically, when you have a strain representing compression or tension, okay, I'm not going to say like positive or negative because it depends on the context, but yeah, you'll know intuitively that's a compressive strain, and at the bottom, that's a tensile strain. Okay, so strain just means how stretched or squashed your beam is, basically, right? There's the formula for it. I think it's like delta L on LO, right? So it's just, it's unitless, right? Because you have meters and you divide it by meters, or you have millimeters and you divide it by meters, and it's just a ratio of how much you've deformed your beam versus the original length, right? Just keep it simple. That's all it is, okay? So when we get to ultimate stage design for concrete, right? Okay, let me just draw out a little diagram. I'm gonna kind of information dump a bunch of stuff, right? So we have stage 1, 2, and 3 for concrete, right? Which is your uncracked stage, you have your cracked stage, and you have your ultimate stage, right? So this just means how much strain you're putting on your concrete beam, right? And as you increase your strain, it undergoes more and more stress as a result, right? So let's say I have Rio at the bottom, singly reinforced concrete like this. Our neutral axis in uncracked concrete, so when you're basically not loading it at all, is, so if there was no Rio, right, you'd expect the neutral axis to be in the middle. So I should talk about what the neutral axis is. The neutral axis is this thing. It's where there's 0 strain. That's the definition of neutral axis, okay? So, so like on a stress strain graph, right? Neutral axis is where there's 0 strain. Got it? If the Rio wasn't there, you'd expect the neutral axis to be right in the middle of where that concrete square is, right? Okay, but the steel is stiff. It's a stiff element, and it attracts the neutral axis down. So the beam actually wants to bend here, bend about that axis, right? But that's only when it's uncracked. So what happens is when your beam's cracked, you don't consider any of the concrete in tension. Like, it will contribute a little bit of tensile strength, but concrete's really bad in tension. You can't rely on it. So we just say that it doesn't exist. That's the most conservative kind of assumption that you can do, right? So if I mapped that, and its strain, right? Its strain looks like that, okay? If I mapped its stress, the concrete doesn't have any stress that it can contribute underneath the neutral axis because it's all in tension, right? The steel does though. How am I going to do it? That's that way. That's that way. So that's the steel's. That's the steel's line, basically, right? And that's the stress that the steel can contribute. Okay. That's the crack stage. So how we apply this, right? Is stage 1 and 2 is used in serviceability design. Which we will get to later, okay? But stage 3 is your ultimate, how am I gonna lay this out neatly? I might move this down here so that I can draw the, yeah, that's good. Okay, so the ultimate stage of design is where basically your concrete is really fucked up. And so the neutral axis moves up even more because more of the concrete is broken, right? So how this looks on a stress strain graph is like this, okay? The stress, I'm gonna carry the neutral axis across. The stress is parabolic, right? Don't get scared, okay? But it's parabolic and it looks something like this, right? Sorry, if it was parabolic, it also goes down to the neutral axis, like that. Okay, cool. So that's what the actual theoretical strain and stress curves look like, right? But in the concrete code, right, AS3600, we make some assumptions that are a little different to this, okay? The first one is like, okay, at what point do we consider our analysis? Like, there has to be some point like that we consistently agree on that we analyze our concrete beams to go to. So does anyone know what strain value we take as the ultimate strain?
0.3.
Very good. Where do I mark that on the graph? Where do I mark that on the graph? At the top, very good. So the ultimate compressive strain is 0.003. So you're going to see that number a lot, especially once you do a bunch of practice examples. That's that point there. So that's every single time we do flexural design, that's the assumption we go with. We say that the concrete, like in reality, it can actually go beyond that point in compression, but that's the point we conservatively agree on is like, okay, we're not allowed to take the beam any further, okay? Okay, so 0.003. In terms of the parabola you see, that's probably different to what you've seen in your workshop examples, because in AS3600, we actually simplify the shape of this parabola to a rectangle. So it's called rectangular stress block. It's the method. Stress block. And this is a method, right? And it's an assumption, it's a simplification, but it's going to make our lives a lot easier. So it looks like this, okay? So we have just taken that parabola and we're saying it's actually a rectangle, but we trim off a bit of the bottom, okay? So what does that manifest into? We have these reduction factors in the code, right? This is gamma dn, right? Again, dn is just depth from the compressive fiber to the neutral axis like that. Gamma is a reduction value. It's something in the ballpark of 80%, okay? So like visually you can see that. So there's dn, 80% of dn, trim 20% off the bottom of that, and then that's gamma, okay? And then we have here, so normally, right, if I draw the parabola thing again, the parabola is the peak of that parabola, and that's F-C, right? That's the maximum compressive force that the concrete can take. But we're gonna reduce that a little bit because actually our rectangle overlaid looks like this. So we're gonna reduce that a little bit, right? So that reduction factor is called alpha 2. Okay, alpha 2 is also in the ballpark of 0.8. Yeah, I'll tell you the formulas for it later when we do the questions. But just understand, intuitively, alpha 2 and gamma are just reduction factors, right? For the sake of simplifying our analysis, so that we have a nice rectangle. Yeah, make sense? Cool. So that's used in flexural design, which is also strength design. Flexural strength design. Now, similar triangles, steel yield. Oh yeah, so basically, once we find, am I overcooking this? I gotta always take a step back and think that to myself. So essentially, how we do flexural design, the first step, you'll see later, the first step is to find the depth to neutral axis. Once you've found the depth to neutral axis, we have to check our steel yield assumptions, okay? So what does that mean? If we have a singly reinforced concrete beam, which just has the tensile Rio, we assume the tensile Rio has yielded, right? Which means that the stress that it experiences, steel tensile, is FSY, which is 500 for N-class bars, right? Compressive bars, we assume that they're not yielded. So therefore, this is not FSY, basically, right? So it's some number less than FSY, if we assume that. So it'll be like 200, for example, rather than 500. So does anyone kind of know why we assume that? And an easy sanity check, or like a logic check, to make sure our assumptions make sense. So for steel to yield, right? Think back to the bending theory, engineer's beam theory. Let me just draw a so this is the stress strain curve for steel, right? We want the steel to reach this point here, right? Which is the yield point, because that min-maxes the amount that the steel can contribute, right? In terms of our bending resistance, okay? So what has to happen in order for it to get to that point? Anyone know? So basically, the more that it has strained, the more likely it is to yield, right? So talking back at our beam here, right? Let's just pretend that there's steel here, and for whatever reason, the neutral axis is in the very middle of the beam, okay? So basically, if there was steel at the very outer fiber, right, versus steel, okay, actually, let's simplify what I just said. Okay, if there's steel at the outermost fiber versus steel at the neutral axis, right, which one's more likely to be yielded?
Outermost fiber.
The what, sorry?
The outermost fiber.
Very good. It's being strained more because it's further away from the neutral axis. If it's at the neutral axis, in fact, it's not being strained at all. It's just that it's contributing is 0 because the strain is 0. So the more strain it experiences, the more stress that it can contribute, right? So with that in mind, and the neutral axis is here, right? So the tensile bars, are they further or closer to the neutral axis than the compressor bars? Compressor bars are the one on the top, right?
Further.
They're further, so they're more likely to be yielded, right? So once you start getting into this region, I'm just going to draw it like kind of indicatively. Once you get to like a region around here, there's a chance that your bars have yielded, right? Up the top, it doesn't really happen because there's not really enough space for the distance from the neutral axis to be far away enough for your bars to be fully yielded. But that's the way you think about it, right? You think the further it is from the neutral axis, the more likely it is to yield. Got it? Am I making sense? I don't know.
So in the exam, you're doing this question,
yeah,
and then those assumptions don't meet, you fucked up, you have to redo it.
Yeah, but if you go with these assumptions, 99% of the time you'll be right. But you still have to check it. Yeah. And the way that you check it, it's probably easier to show in an actual question, but you essentially do you do your strain curve, and then you do similar triangles. You compare like, okay, the slope of this triangle is the same as like this triangle, kind of thing. Oops. Cool. Sorry, I know there's a lot of information. Making sense? Okay, let's keep going through that list. Stress to force conversion. So basically, yeah, that's fine. What's the formula for stress? Anyone know?
Force over area.
Very good. So stress is force over area. Now you're going to see this a lot, right? Because we're going to need to convert from stress to force and vice versa, right? Actually, usually it's the other way around. So if we rearrange this, right? Force is equal to stress times area. You're going to see that for most of the equations that we use in this topic. So just keep that in mind. That's always the thing you kind of fall back on when you're deriving your beam or whatever you're going to do, right? Next is force and moment equilibrium. Okay, so basically, right, say we have a scenario here. So we have a beam, and the top of the line here is the top of the beam. The bottom of this line here is the bottom of the beam, right? And what we're saying is if we have two forces, right? If we have a force up here and we have a force down here, we can find out the moment a couple of ways, right? 2 ways, let's just say. We can take the sum of the moments. Let me just get rid of that for a sec. Method 1, we can take the sum of the moments about the neutral axis, okay? So if we take the sum of the moments about the neutral axis is equal to, not equal to 0. Usually you sum them. You do force 1 and force 2, right? Let's just call that D1 and D2, right? So you go force 1 times D1 plus force 2 times D2. The reason you add them together is because using the neutral axis as like a point of reference, they're both spinning the same way, right? Yeah? Am I making sense? Okay. So that's one way you find the concrete's resistance, right? You do the sum of the moments about the neutral axis. The other way is you take the sum of the moments about. Normally, what you do is you can do like you can take the sum of the moments about force 1, okay? And then that just means you only consider force 2 and you add d1 plus d2. Do you know what I mean? So there's like different ways. So if you look through like the workshop examples, some people do it the first way, some people do it the second way, but it's the same number that you get in the end, if that makes sense, right? Because you just, yeah. Because if I'm using here as a point of reference, right? This is the only force that doesn't have a 0 lever arm, and then you combine those 2 lever arms together. Got it? Some other people do it like some of the moments at the top of the beam, but then it gets confusing because then you have to subtract the forces from one another. Because if you take the top of the beam as your like point of reference, right, then this arrow is making it spin one way, and then this arrow is making it spin the other way. Don't do that. This is going to make it more confusing, right? Got it? That's kind of how we do it. Last little equation I might just quickly mention, which will come up. What am I saying? Okay, elastic modulus is stress over strain. This will come up a little bit as well, but this is like one of those basic formulas we use a lot, right? Just like how we use forces equal to stress times area. Cool. So I realize we're at nearly 7 o'clock and we haven't done any questions, but maybe we can decide what questions we're gonna do. So there's a couple options. We can take a break now and then do the questions, or we can do a question, but a question is not gonna be short, right? So up to you. What do you guys want to do? You want to stretch or?
We're good.
You're like, let's just fucking do it, right? Great. So now we're up to picking questions, okay? So here's like, okay, one thing before I get into it, right? I just want to comment. If you've seen the concrete code, it was updated in 2018, right? So I wouldn't trust any past papers you see earlier than that, because if you see a past paper earlier than that, it's using the old code, right? Which means some techniques, some like lines of working will be wrong for our modern standards, right? Therefore, we should only rely on papers that are newer than that, right? So the ones that I've included in that folder for you guys is 2019, 2021, 2022, okay? So I'll give you an idea of like kind of the patterns you can kind of see, right? The blue one is flexural related. So flexural design is a little bit different to a flexural check, right? Flexural check is basically, here's a beam, what are the loads, and how strong is it, right? Flexural design is, here's a beam, what are the loads? Now you design the shape of the beam, right? You design how big it is, right? So the reason why the 2019 paper only has these 2 questions, right? Question 4, question 5, is because it takes longer, because you don't know the size of the beam. It's also probably harder for them to mark, because everyone's gonna have a slightly different beam depth, right? So it's a possibility. It's something that could come up, but it might not necessarily. But it's all under the same topic.
Which do you think is harder?
Definitely the beam design. Yeah. The other thing is shear reinforcement. So shear reinforcement, it uses completely different methods, but it's still part of kind of beam design. The theory for shear design is harder to understand and also explain than actually doing a shear question. Doing shear questions generally are okay, right? And then serviceability, similar idea to shear, where the theory is harder to explain than actually just following the steps. Last thing is columns, right? Which might come up. Columns are basically flexural design on steroids, because it's got everything that's hard about flexural design and then adds like a little bit more to it, if it makes sense. So based on what I just said, you can pick any of these questions. We're going to run through 2 of them today. Okay, based on what I said, right, I'm going to get you to put your hand up to vote for them, right? So who wants to do flexural, which is the blue one? You doing this course, Andy?
Yeah.
Oh, yeah?
Yeah, why do you?
Oh, sorry, I thought you were like,
You think I'm sitting in my
I thought, you're a second year, aren't you?
Yeah.
Oh, you're doing this course. Oh, I thought you were just troll voting. Okay, sorry. Okay, sorry, so let's do that again. So, flexural design. Hands up. Okay, put your hand down, please. Shear design. Who wants to do? Okay. Serviceability design. Who wants to do? Okay. And then column design. Okay. So we might start with okay. My idea is we will do a flexural design question, and then we'll do a serviceability question, and then I'll just talk briefly about how columns work at the very end. How's that sound? Great. Okay, so let's pick one. If we do a flexural design question, we might be here until 10 p.m. So let's not do that one. We can do this one or this one. How am I going to choose? Okay, let's just do the harder one. Let's do the 2022 where we have to add compressive rear. Let me find it real quick. Mm-hmm. 2022 practice. Okay. All right. So, basically, here's how it works. You're going to be presented with this question, and then you might not know where to start. So I'm going to start interrogating you guys. Where would you start? Anyone know? Oh, sorry. Let's read through the question. That's probably a bit more fair. Okay, sorry. So we have an unfactored uniformly distributed dead load, including self-weight, of G equals 15 kilonewtons per meter. We have an unfactored uniformly distributed live load of Q is 20 kilonewtons per meter. And we also have 2-point loads, right? Which are live loads of 18, which you can see here. Dead and live loads are always applied over the entire length of the beam. Yeah, la-di-da. The cross section is shown down here, right? Use these things. Sketch the bending moment and shear force diagrams for the beam, indicated values of bending moment and shear force. Okay, so it's basically saying sketch the bending moment and shear force diagram. The next part is calculate the ultimate bending capacity of this section. And then compare it with M star to see if the beam will break. And also, does the beam satisfy ductility requirements, which I haven't talked about yet, but I will. If the section doesn't meet ductility requirements, how much compressive reo do we need to add to ensure the ductility is 0.3? Great. So, they don't want you to redesign the beam and not give you the amount of compressive reo they're going to add. So then there's a new section which shows 4.3, right, which is the third part of the question. Okay, so going back to what I was saying, what would you guys do first in this scenario, Andy? Sorry?
Load combos.
Yeah, very good. Load combinations, right? So basically, just to give you like a bit of an idea of what when I say like terms, right? When I say left-hand side and right-hand side, I'm referring to this equation. So this is the capacity equation, right? It's saying that the external loads have to be less than how strong your beam is, right? I always start with the left-hand side pretty much. I always start with external loading. It won't take as long as your other side, and also I don't know. I just kind of get into a pattern. Some people do it the other way around, but most of the time I feel like people do left-hand side first, right? But they're two completely separate calculations, right? So they don't really depend on each other. Yeah. So I'm going to do left-hand side first, which is your load combos, okay? So, okay. Basically, right, I'm going to simplify the beam. I'm going to draw it as a free body diagram, right? Free body diagram 1. Okay. I'm going to copy this. Free body diagram 2. Okay. Okay, so in my first free body diagram, I'm representing the first load combination, which is 1.35 G. In the second free body diagram, I'm representing the second load combination. If you guys have seen other load combinations in steels before, like with wind, just know that it's outside of the scope of this course. We don't deal with wind design here. Typically in industry, concrete design only uses these two load combinations, and then you check for earthquake design separately. But steels is more governed by wind usually. Yeah. So, why does anyone want to have a crack at why I've drawn it the way I have, where one has the point loads and one doesn't?
Was it because the point loads were mentioned as being live earlier?
Yes, very good. So one is dead load only, and the other is dead and live load, right? So, with that said, right, basically, this load here, we're going to call W star, okay? And that's going to be 1.2 multiplied, and this is a uniformly distributed load, by the way. 1.2 times 15, right? Plus 1.5. Oh, sorry. No, wait. Just trolling. Yeah, that's better. Okay. So 1.35 of just the uniformly distributed dead load, because that's the only dead load in our loading situation, right? Yeah, next, W star is 1.215 plus 1.5 times 20, right? I'll get what those are equal later, but what do we multiply these live loads by? Sorry, the live loads are 18, right? The point load live loads are 18. What do we multiply it by, do you reckon?
1.5.
Very good. So I'm going to call this P star. 1.5 times 18, right? And it's the same as that point load. Okay. Have I typed this in my calculator already? Yes. So this is 20.25 kilonewtons per meter. And this one is, what is it? 48. Yeah, it's 48. And then the point loads are 27. Makes sense? So this should be enough, like this example that I've just run through, should be enough for you to kind of wrap your head around load combinations. Right? We have different loads, some are dead, some are live. How you combine them, you need to basically set up two different free body diagrams and then work it out that way, right? That's the idea. Now, the thing is, right, there are some situations where it's ambiguous which load combination is going to govern. So when I say govern, it means it's going to give us the max bending moment, right? But you can kind of tell straight away which one's going to govern, right? Top or bottom? Bottom. So we don't even need to justify it if it's really obvious. There are some situations where the dead load's so high that like 1.35 G, like multiplication factor, overpowers the live load, right? But here, that's not the case. Okay? So we say that this governs, which means we're going to use this to draw the shear force diagram, bending moment diagram, right? Okay? So shear force, actually, before I go into shear force, let's do the reactions, right? So there are a few ways, there's two ways to get the reactions, right? One is your classic like Eng 1300, some of the moments, and then some of the forces to find the other reaction for these two reactions. But visually, right, we have an evenly distributed beam with evenly, like, symmetrical loads, right? So the left and the right support are taking 50-50 each, right? 50% of the loads are going left, 50% of the loads are going to the right. It's simply supported, right? So all we need to do is find all of the downwards forces, and then 50% of that's going up in the left support, 50% of that's going up in the right support. You're allowed to do that. That's like a, yeah. So we have to find the total loads, right? We go the 2-point loads, and then we go 48, which is the distributed load, But what am I missing here? That's not the total load, is it? Sorry? Oh, sorry, I think it's including self-weight, right? Yeah.
48 is per meter, I guess.
Exactly. So if this is in kilonewtons and this is in kilonewtons per meter, what do we need to multiply it that way?
And then of the beam.
Exactly. We need to multiply it by something that has the units of meters, right? Which is the length of the beam. So, which was, what was it? Okay, wait, let me just write out the geometry, otherwise I'm confusing myself. This is 2 meters, this is 2 meters, this is 5 meters. So the whole length is 9 meters, right? Cool. I don't know what that is. That's 4, 8, 6, I think. Right? So each support is taking 2, 4, 3 going up. Right? Make sense? Cool. So we're going to need the information for our shear force, right? So normally I do shear force going left to right. As so. So basically at the support it jumps up by the amount that the reaction is pushing up, right? That's 2, 4, 3. Distributed load causes our beam to go down like that, right? And that slope is W star. Does that kind of make sense? That's kind of how you would think about it, right? And then we have another point load, right? Which means there's a discontinuity in our line and it shoots it down, right? How much does it shoot it down by?
27.
Exactly. Which I won't mark yet, but just how you scribble your original shear force diagram. We know that the beam is symmetrical, right? So it's got to connect to the 0 point in the middle, and then it's symmetrical. So we kind of just mirror the shape. And then at the end we jump back up to 0. So that's negative 2, 4, 3, right? Okay, let's find this exact point, right? So the way that I would do this on my calculator is you have that initial point, and then it has that slope, right, of 48, and then how many meters does it travel going down? 2, exactly, very good. So that's how you would calculate that point, right? Which is 147. And then we know that it jumps down by 27, right? So then that point is 120. Get it? That point is 0, etc. Right? So this is the inverse. This is negative 120, and this is negative 147. That's shear force diagram. Now, the way that I like to do the bending moment diagram, which is the fastest, is you find the area underneath the shear force diagram, right? So we can break this up into easy shapes, right? There's 2 ways to do it. I'll show you the trapezoid method, right? So I'm going to divvy it up by, we have one shape here and one shape here, right? First shape is a trapezoid, and the second shape is a triangle, okay? So area of a trapezoid, the way I like to think about it is the average of the 2 heights, right? Multiplied by that length. So, Janice, can you come up?
Huh?
Can you come up?
What?
Oh no, just come up. Please, sorry. This is not fair. Right? I was going to get Caden, because Caden's really tall. But, so if we take Janice's height, right, and we take my height, and then basically we average it, it's going to be like somewhere here, right? And then let's just say there's 1 meter between us. Area of that trapezoid is that average height multiplied by that, right? So it's kind of like base times height. Sorry, you can see that. My bad. Does that make sense though? That's like the way that I remember it, right? I was gonna get Kate to understand, but instead of you, but yeah. Yeah. So with that said, right, average height, we know the average formula is 243 plus 147. So the 2 things divided by 2, right? If you add them together and divide it by 2, that's like an average, right? So that's one dimension. That's the up-down dimension. Left-right dimension, who knows the length that we're multiplying? 2, very good. So that's that shape. And then area of a triangle, half base times height, right? The base is, let's be careful here, 5 divided by 2 is 2.5. Base is 2.5 times height, 120, like that, right? I'm gonna get my calculator out, so I did it differently to my notes. Cool. That's 390 kilonewton meters. It's kilonewton meters because the up-down dimension is in kilonewtons, the left-right dimension's in meters. So if we're finding an area, it's kilonewton meters, right? This is the net unit, right? And then area 2, this triangle, is 150 kilonewton meters. Okay, great. We have enough to draw our bending moment diagram, right? Sorry, I normally draw it underneath as well, so everything lines up nicely, but I've run out of space. Oh, you know what? I can fix that. Well, if I go like this, just make it smaller. So I'll just draw the bending moment here. Actually, because the bending moment calc is different to the concrete strength calc, we can take a break after this, after we do the bending moment diagram. Okay, so basically, how we draw a bending moment diagram is the shear force is the slope of it, right? So when we have 0, we know that's gonna be flat, right? You might have seen bending moment diagrams where it's like positive is up here before, right? That's intuitive, that's what you do in 1300. But as like structural engineering practice, we take positive as the bottom side. The reason for that is it shows the actual direction that the beam will sag. It just makes more sense, basically. If you have positive bending, your beam goes down. So actually every bending moment diagram you'll do from now on is gonna show positive going downwards. Like opposite direction to the shear force, basically. So shear force is, positive shear force is up, positive bending moment is down. Makes sense?
They mark you down if you fuck it up in the direction.
Maybe I don't think they'll mark you down actually, but it's good practice. I'll do all your practice questions this way. Yeah. So basically, with that said, so if this is 0 slope, right? This is the highest slope over here, correct? And then this is like medium slope. So how we're gonna draw this is like this. Shit. So there's, I didn't draw it very well, but there is a discontinuity there. You know what, I'm gonna redraw it. I'm gonna exaggerate it. And that's 0 bending moment there. But do you see how there's a jump? Because there's a jump in our slope amount, right? That's what the bending moment's gonna look like, right? So, basically, it looks like this. So the to find the bending moment here, that's that area 1, and then to find the bending moment there, it's 1 plus 2, right? So 1 is 390, right? 1 plus 2 is 390 plus 150. We found these areas before, right? I mean, not areas, bending moment amounts, which was the area of the shear force diagram, right? So that's 540, which is our max bending moment, M star, that we're interested in. So that's how we find the left-hand side, basically, right? Cool, let's take Smoko. Yeah, we'll come back in 3 minutes, but if you need, stretch your legs, walk, get some water, stand up. Yeah, we'll chill. At the very least, I would recommend standing up because we're going to be here for a while. Yeah. Yeah.
At this time.
He is interested in water engineering. Do you have something to share? Stretching.
Oh, sorry. Oh, Jack's trying.
This is Janice. the start of the water is up here.
Really? Yeah. Sorry? Wait, Oricon. I don't know Oricon to water. They do a lot.
I think it's all under the.
Water consulting.
Consulting.
I tend to work in like on the side, like Sydney water or something like that. But
Yeah, that'd be more government.
no. Oracle works a lot with Sydney water.
Oh, sorry.
Yeah. Oracle is well, not a lot, but like for the design phase, we usually visit the site and like check out.
I've just been saying it's internship, but it's like a definite. Oh wait, no.
And just like
So I didn't know the difference until what you're gonna get
Yes.
that.
No.
That was like wait.
Yeah. That's just internship. That was the exact moment I realized.
That's really cool.
That was the exact moment.
Sorry? The job was that hard?
It's like what's the
Oh, well, more
I mean, it's good
specifically,
idea.
like, I work in the
I don't really recommend it.
But it's good at knowing
Is wastewater.
I didn't know wastewater like this too was boring.
Yeah,
well, it depends on like
I'm doing those with Math 2018.
Oh,
There's a lot of choices.
Yeah, not too bad.
Personal
How are you?
Yeah.
You're right, thanks. Big
Oh,
time.
So
yeah.
you're oh, okay, so like wells as well as
Recommendations are really good so far.
how to
Wait, what subjects are you doing?
wastewater.
Right now, concrete dozen 2002.
Oh, nice.
Yeah, but there's also like treatment
Well,
as
not
well.
nice. I haven't had testing yet. I still haven't had testing.
Have you done the courses yet?
I'm doing transport. I'm doing different transport.
So that's my
Oh,
last
Yeah, transport.
Probably like them.
I didn't like transport.
It'd be crazy if you didn't like it.
Yeah, that would be good. It's really good. I don't know.
I think gas with everyone into thinking it was good. Because you really enjoyed it.
I
I think you gassed it everyone into thinking it was a really good subject.
transport.
Yeah.
A lot of people don't like it, but it's
I
good.
guess like the team I'm in was
Yeah, a lot of people don't really
like,
like this. Like transport. Was that the same?
Those parts I like.
No, like there was a consensus when you did it with others.
People just thought it was like middle of the line usually.
Right.
It's quite different. There's no there's mathematical modeling, not really physics, which I think throws people off.
There is some physics, some kinematics. Not very much.
Oh, it's around the bend.
It's not like the rest of engineering.
I don't think it helps that the midterm was also very long. So people probably just like hated that exam.
Oh, the midterm is awful.
Oh.
Because she didn't
54.
she didn't mark she didn't mark it properly, they didn't mark the working out.
It was a lot of
Then they marked the working out afterwards. I think my mark went up 3 times because they kept adding marks because they didn't mark it right the first time.
Great.
They just marked the Moodle answers, but like, most people's Moodle answers aren't going to be right. It's like, so you need to wait. It's like they don't carry forward errors or anything, so it's just, it's close.
So badly doesn't this one.
But you know,
Anyway.
How was the requirement process?
it's the first time I've gone to lectures. So.
I actually
Never done.
Well, do these ones are good to go to.
Yeah.
She calls you out if you don't
because I wanted to
go to lectures. Like on the move, she asks questions like, how come I never see you in lectures? She like has like a sassy response.
She's so sassy. She's
She's so funny though.
Yeah, she's
It makes
very
the boss
sassy.
pretty entertaining.
She's very sassy. Very funny.
All right, sorry. Let's go back to it because we got limited time and all that.
If you don't want to do transport, you're only do that.
Okay.
Considering doing the extra stuff, the extra transport.
Oh, that's in kilonewton meters, isn't it? Okay.
So not as much as like.
Let's continue. So, left-hand side, done. Right-hand side, this is where we dive into neutral axis. Oh, sorry, I'm gonna add more pages. Okay. So, let's go back to the question, right? Pretend you're in this exam and you just solved the bending moment diagram and the shear force diagram, which is the first little like sub question, right? What would you do like in this position moving forward to like complete your exam? Any ideas?
Find the
That's good, but there's an in-between step that I would do first. The next one I would do is material properties. Okay, so do you remember how I was talking about gamma and alpha 2 before? So that's what I'll do next. There's formulas for it, right? Which you actually need to use for this question because it has an unusual concrete MPA. So here's the formula. Has to be, I'm gonna put this over on the right. It all has to be under point, over. It's greater than that, yeah. I've never seen it less than that. I think you need like 200 MPa concrete or some crap to go over that, which is like incredibly, I don't think it exists, to be honest. Okay. So those are the formulas basically, right? And the reason I say that is because standard concrete, like that you would get from like a concrete supplier, right? It comes in 25 MPa, 32 MPa, 40 MPa, 50 MPa, whatever, right? And on all of your little tables that you might put on your cheat sheet, the alpha 2 and like gamma, like cheat sheet, like quick values that you can quickly just get without punching in the formula, it's going to be one of these MPAs, right? So because I gave you 38, that's really weird. You're gonna need to type in this calculation, right? So I got 0.875, 0.793, right? Again, to make sure you're not going insane, these should be around the ballpark of 80% or 85%, right? If they're not, you typed in your calculator wrong, okay? So, like you said, Andy, the next step is find DN, right? So we always find the depth of neutral axis next. And the way that we do this is we utilize the sum of the forces calculation. So how do I represent this? Okay, I might draw, yeah, that's probably the best thing to do. So draw out your cross section, draw out the strain, draw out the stress, draw out the force. So get into the habit of doing these things in this order, because then you'll be able to do it quickly, right? So neutral axis will be somewhere up here, okay? They give you a bunch of dimensions, which I'll just draw up. That's 350 is the width, right? From here to the rebar, which I haven't drawn in yet, is 485. And then from the rebar to the bottom is 65. So rebar, I mean, normally they draw it as bars, but they just draw it as a straight line here. It doesn't really matter, because they give you the tensile steel area, right? Am I missing anything? Not really. Great. So when you're drawing your strain curve, you basically need to make sure the neutral axis roughly lines up, like the area of zero strain lines up with wherever you've drawn your neutral axis to be. And then that number that we were talking about earlier, make sure this is 0.003, right? And then later we're gonna check the steel, right? And find the strain of the tensile steel. Okay, next we draw the stress curve. And the stress curve, I'm just gonna carry through the neutral axis. The stress curve, we have the compressive concrete stress, and then we have the tensile steel stress, right? We're gonna assume that the tensile steel is yielded. So the stress acting at this point is FSY, which is 500 MPa, right? In terms of the concrete, I'm going to zoom in a little. And I'm going to move this up. I always do this. I don't give myself enough room. This is going to be alpha 2 FC. And then this is going to be gamma DN. Like that, okay? And then in terms of forces, right? Same position. We're going to put the tensile steel force in line where we've put like the steel, like same depth and everything. And for concrete, in the middle of the rectangular block that we drew, right? So that should be at the middle of gamma DN. Make sense? Oh, that's it. Cool. So, let's calculate it. So to find DN, we need to take the sum of the forces, which you can see visually here, okay? So we're saying that the compressive concrete is equal to the tensile steel, okay? So we can break this down further, right? So it's basically that left arrow is equal to that right arrow, okay? We can break this down further because we can find what the formulas are for both of these components, right? The compressive concrete, we basically turn this into a rectangular stress block, that little thing that I just hatched in purple, right? So it's alpha 2, FC, gamma, dn. Am I missing anything, guys?
Right.
Very good. So, if I'm looking at my beam in 3D like this, right? And we've got our steel, and we've got our concrete. We're turning this uniformly distributed load or area, right, into a singular point load in the middle, right, CC, okay? So we're gonna need to multiply it in 3 dimensions, right? Well, 2 dimensions and a stress, right? This dimension is gamma dn, so the up-down portion of this rectangle is gamma dn. We need to multiply it by the width of the beam, which is b, right? And then we need to multiply it by kind of like the amount that that's that stress block, the magnitude of that of that block, right? Which is represented in that axis, like how far it comes out of the page, which is actually a stress, which is alpha 2 F dash C. Does that intuitively make sense now? Probably not. But what we're doing is essentially what I was saying earlier. The force of this concrete, CC, that's a force, is just the stress times the area, right? The stress is alpha 2 FC, right? The area is the breadth multiplied by gamma dn. That's the area that's acting on this block here, right? Make sense? Like, it's a bit of a mindfuck the first time you see it, to be honest, but it will come intuitively. So similar idea, right? So force is equal to stress times area, right? So to find the tensile steel force, we assume that it's yielded, so FSY, and we multiply it by the amount of tensile steel that we have, which is given in the question, right? So now it's just a matter of subbing in every number except dn, right? The width was 350, the stuff's given, this we've calculated, they were, this one was this one was this, 38 MPa, right? The only unknown is dn. You'll find that whenever you do a singly reinforced concrete beam, meaning just the tensile steel, no compressive rio, this dn value is not going to be hard to find algebraically because you're not going to have a quadratic equation. Once you introduce compressive rio, it's going to be a quadratic equation now, okay? Because you're going to have more than one thing as a function of dn. Once you have more than one thing as a function of dn, it's going to be quadratic. The only thing that's a function of dn right now is the compressive concrete force. Does that make sense? Yeah. So this is literally just a matter of divide the right-hand side by these components of the left-hand side, and then we find dn that way. What have I found it as? 201.55 mil. So dn is always from the compressive fiber, right? Most fiber down to the neutral axis. Okay. So the reason I say that is because imagine a cantilever, right? Cantilever beam looks like this, right? If I put a point load on it, it's gonna deform like this. Now, is the top or the bottom in tension? The top's in tension, which is different to a simply supported beam, where the top's in compression. So dn, if I was to find it for this beam, dn is actually from the bottom. Yeah. So, don't get tricked. Okay. Everyone got it? So, we've found dn. Our next step, step 2, is check steel yield assumptions, which I'll just write as check steel yield, right? So, I'm just gonna copy this from earlier. This is, you don't have to do this in the, what am I saying? You don't have to do this in the exam, but I'm just showing you because it's easier to explain this way. I'm gonna repaste this strain graph here, right? So, we're checking that this number, right, is greater than our steel yield limit, right? Because if it's greater than this, then our stress in our tensile steel is yielded, which is 500 MPa, right? How do we do this? So we basically can find an equation for the left-hand side and one for the right-hand side, okay? Let's start with the left-hand side here, right? We can utilize similar triangles, right? Triangle 1, triangle 2, okay? We say, with similar triangles, the slope of both the triangles are equal to each other, right? This is equal to this, right? Slope-wise, right? Rise over run is equal to rise over run. So let's do the rise of, actually, I drew that one way, but I'm gonna do it this way, right? So visually, just keep that in mind. So for the top triangle, right, what's the rise? I'm gonna draw it, but someone say it, please.
201.55.
201, what, sorry?
201.55.
Oh, yeah, very good, that's dn, yeah. So I'll just write dn first, but I'll sub it in. But yes, the rise of that triangle is dn, right? The run, right, run, left to right, is 0.003, right? Because that's the run. Keep in mind, we're just talking about this right now. Don't worry about this yet. This is like trippy because you can't really do this in mathematics. There's a line break between these two equations. Okay. This other triangle here, right? That one. What's the rise? Okay, I'm gonna bring them back. Sorry, I'm gonna bring these over. It's gonna take a sec, sorry. Boom. Okay, so what's the rise?
5 minus dn.
Very good. So the reason for that, you can kind of see it here. You go down, and then you subtract dn, right? Leaving you with this blue line. Okay, that's the rise of that triangle, right? Okay, the run is epsilon st, which is what we're solving for, right? We cross multiply, right? Multiply the fractions on one side over, and then vice versa. So dn, epsilon st, and then 0.00345 dn, right? Divide dn over. Okay. Once you, like, I'm just doing this really slowly, but once you do this enough times, you'll also be able to find formulas for similar scenarios. But yeah, like you said, Andy, it was 201.55. Yeah. And this whole thing is equal to 0.0042. Okay. So that's this, right? We're solving, oh, fuck. Okay, bear with me. Okay. Here's why, right? This is the steel yield limit, right? You know how I was saying earlier that that the elastic modulus is the stress over strain, right? We're going to rearrange this for strain. So strain is equal to stress over elastic modulus, correct? we know what this is for steel because we have a limit and then we have the elastic modulus of steel, right? So we're doing 500 over 200,000 MPa, which gives 0.0025. Okay, so that's the limit, right? Now we're going to check whether this is true. If this number, let's do like this, right? If 1 is greater than 2, then we've yielded. Therefore yielded. Because it's greater basically, right? Makes sense? Excellent. Oops. Okay, so that's that. Okay, what's the last part of the question? Oh yeah, the last part of the question, this part of the question is find the moment. Find the moment resistance. Again, I'm just copying this over so it's easy for you guys to like kind of understand. But you don't have to like redraw this every time unless you want to, which you can. So you know how I was saying earlier that if we take the sum of the moments, we can take it like at the neutral axis, or we can take it at one of the forces, right? So, which one should we do? Let's take it at one of the forces, right? So, CC, we never calculated CC. So CC is equal to alpha 2, FC, all that, right? Gamma, dn, B, right? So alpha, okay, give me a second. It's all this shit basically. Copy. It's like all that, right? Okay, sorry. Let's do like this, right? All this, and now we know that dn is this, right? Make sense? So here we've got the force of the compressive concrete. We've just put that in. Now, what lever arm do we need? You don't have to say the number, but like if someone can describe the lever arm that we're gonna take. Farhan?
Distance between the forces?
Exactly. So the lever arm here is gonna be the distance between the forces, right? It's gonna be here down to here, right? So I think relatively intuitively, you can get down to the tensile steel, right? What's a little bit unintuitive generally is what is this distance here, right? To the middle of the concrete. Yeah?
Is it gamma dn over 2?
Very good. So some people might originally think it's dn over 2, but remember that force isn't exactly halfway down to dn because we have that reduction factor. Just remember that this used to be a rectangular distributed stress shown like that. So actually we need to put that gamma reduction factor in as well. So the lever arm is 485 minus gamma dn on 2, right? And we kind of have gamma on hand here, don't we? And then we also have dn on hand. So now we can just chuck this in the calculator. And do you guys know what units this will give? So let's just say we find some number. Anyone know the units? Yep. Basically, we're working with this set of units, right? MPa, newtons, millimeters. And when you work with these, you're gonna get those basically, right? This set of numbers, this set of units will all like talk to each other, right? So you're gonna get some number that's gonna be fucking huge on your calculator, right? What I like to do is I like to punch in the calculator and then divide by 10 to the 6. Now it's gonna go down to kilonewton meters, basically. And that is kind of the units that we use on our bending moment diagram. So it's kind of weird because the units that we get from this calc are going to be different to the units that we get from just doing bending moment diagrams, if that makes sense. So now we're actually comparing this number to the one that we got from the bending moment diagram. Okay. Next we're going to find what phi is, right? So in the code, phi can range between 0.65 and 0.85, right? 0.65 is when your concrete is brittle, right? And 0.85 is when it's ductile. So the idea is, if it's brittle, it's going to fail suddenly, and we kind of just give it extra not extra concrete. That 0.65 is saying it's like less reliable than a ductile section, right? So because it's less reliable, we can't count on its actual strength as much. So we only take 65% of what we calculated as the actual strength. But if it's ductile, we say we can rely on it a little bit more, and then we can take 85% of it, pretty much, right? So we can calculate this exactly because there's a formula in the code which lets you do so. So between the bounds of 0.65 and 85, phi is equal to 1.24 minus 13 over 12 KU. KU has a separate formula, which is dn on d. Now we calculated dn, and it was 201.55, right? And d is the effective depth, right? Which is basically from the compressed fiber to your tensile rio's average depth. So like if there's 2 layers of tensile rio, it's right in the middle between them. That's what D is, right? So, oh sorry, what was that number? It was 485, okay? So, if we put this in the calculator, we get 0.7, let's just round it up, 9, right? Yeah, so the idea is that it's somewhere in the middle, right? Based on our depth of neutral axis. So it's not quite fully ductile. They want us to do a moment check, right? So let's just do that. So that number is 0.79. This was, I'm just going to round to the nearest kilonewton meter. If we go all the way back before the break, remember that we found that the maximum moment is 540. So it actually works, I believe, if you type this together. So 80% of that, is it? I can't remember. Let me just quickly check. Yeah, so that's equal to 583 point. Yeah, whatever, I'll just do that like that. So that number on the right is bigger than the number on the left, and that's just saying that the strength is good enough. But there's another part to the question, because the question is saying how much compressive Rio, if we add in compressive Rio, how much should we add in order to make this number, right? It's saying, can we make KU 0.3? Because if we type that in right now, it's 0.416, let's just say, right? It needs to be under 0.36 in order to be fully ductile, in order for you to be able to take 85% of the capacity. But now it's just saying, let's go even further, right? Just to be safe. How much compressive Rio do we need to add in order for you to get the ductility factor down to 0.3? Okay, so what we need to do is we need to work backwards, because it's kind of confusing, right? Because this is locked, right? The effective depth is locked, but dn is not locked. So we can play around dn, basically. So we need to add enough, well, let's just figure it out, right? So let's just work backwards. So this is the last part. KU is 0.3, which equals dn over d, right? And then this is locked, can't move the tensile Rio. So we rearrange for dn. Okay, we want dn at 145.5 millimeters, right? Okay, how do we do that? I'm just going to sketch the section again. it's like ASC is equal to what? AST was 3720 millimeters squared. The neutral axis will be somewhere here. Okay. And just adding in dimensions, this is 65. This is 65. The middle stretch is 420. Okay, great. So, as before, right? Like how we found dn was we took the sum of the forces, right? So now we're going to do that again. Take the sum of the forces. Because if I draw the... One sec. If I draw the force diagram like this, right? We're going to have our... I'll draw it up here. Compressive Rio. We're going to have our tensile Rio. And we're going to have our compressive concrete. Right? And then that's TS, right? So all the compressive force going one way, all the tensile force going the other way, right? So we need to kind of backwork this. So actually I'm going to do this down here because the working out's going to get pretty messy. You know how I was saying earlier that once you introduce compressive concrete, your depth of neutral axis is going to become a quadratic? You're going to see what I mean, okay? So compressive concrete, alpha 2, FC, gamma, dn times B. That's not really, I mean, this is going to change a little bit. dn is going to be unknown, but the rest of the parameters are going to be the numbers that we still worked out before. We're going to have to break down this a little bit further. I'll explain that in a second. And this one is ASTFSY, okay? So, remember our steel yield assumptions. Tensile Rio is far away from the neutral axis, therefore it's likely to be yielded, right? So that's the assumption. Compressive Rio, close to the neutral axis, not taking on as much strain, not taking on as much stress, so therefore likely to be not yielded. Okay, so that's why I've drawn this as sigma CS. We have to work that out. That's an unknown, right? Okay, we're gonna punch in all these numbers that we had before. dn's unknown. This is 350, I think it was. Yeah. ASC is unknown. Oh, no, sorry, my fault. So dn we worked out just a second ago, right? That's that, right? So that's locked. We don't actually have to solve that again. So that's 145.5, okay? ASC will be the unknown. So this is what we're actually gonna solve for. But this was known, 3720. This is known. Okay, let's break down this, okay? So remember this equation, right? We rearrange for stress. It's the elastic modulus multiplied by the strain, right? So if we're talking about the compressive steel, firstly it's steel, so the elastic modulus is going to be 200,000 MPa, right? Secondly, now we have another complication, which is that the strain of the compressive steel is not immediately obvious, right? So if you think about our similar triangles again, okay, so that's 0.003. I'm probably not making any sense. Do you guys have any questions? Sorry, I'll just keep going and then hopefully it will make sense. Okay, so that's the neutral axis, right? That's the compressive steel here. So we want this triangle to equal this triangle in terms of the slope. We say one slope is equal to the other slope. So we can go rise over that big triangle over run is equal to rise, which is, this was like 65, right? Rise over run. Cross multiply, right? And then divide out dn, like that. That's what that is. Got it? So, it's going to look like this. That's epsilon CS, right? And that's going to be multiplied by the elastic modulus of steel. Am I rushing it? Make sense? Okay. I'm going to delete that for now. Okay, so yeah, this isn't easy, by the way. So you'll get this a bit more with practice if you're not understanding it right now. But essentially, know that you need to do this every single time that you have compressive Rio. So learn how to do a doubly reinforced concrete beam in Flexural. Like the method might change a little bit because we're solving for something a little bit unusual. But normally what's presented to you is like, here's a doubly reinforced concrete beam. Find the depth to the neutral axis. So instead of solving for ASC, we'll normally be solving for DM, but same process, same logic with the formulas, right? Okay. Now we know everything because this will be this, right? This will be the number that we solved for a second ago, not that. And then we can rearrange for ASC. And find that, okay? So that's how much steel we need. But that's not a physical thing, right? That's just a threshold number. So that's like the minimum amount of steel that we need, right? So what you need to do is in your, let me show you. Where is it? Here? Basically, I'm looking for like the area of steel tables, right? Those will be at the back of your exam paper. So you'll see a table and it's like 1, 2, 3, there's like number of bars. Yeah, and then you'll have like N10s, N12s, N16s, etc. Right? It's gonna keep going. You'll find a line which has enough, right? So what I did was, this is like N28, and then it's like 4 N28s was enough because that number was 1800. So you want to find a number that's bigger than that threshold number to achieve that amount of ductility.
It's 428, 2480.
Sorry, what was it?
428, 2480.
Oh yeah, I thought it was a bit big. I probably wrote down the wrong one. Was it
4N24.
Try it. It's like 4 N16s or something.
Yeah.
Was 1800?
16, no.
How did I get 1800 again? I probably wrote the wrong.
4N24.
Oh, 24.
Yeah.
Yeah. So there's N20, and then N24, and then you go down 4, and that one's 1800. Sorry. Yeah, makes sense. N28s are huge, by the way. Like if you put N28s in, just in fucking everything, the builders are gonna get really mad at you because they're fucking heavy to carry. Yeah, and they're like harder to bend on site. So if you have like your steel cap boots and then they're trying to bend the Rio into like a non-straight bar shape, it's really hard. Think about like increasing the diameter, like the moment of inertia is like much higher for every millimeter that you add. So like trying to bend those actual bars on site is fucking, it's impossible. So like they like to stick with N24s or lower. Yeah. Cool. Any questions?
6 N20s also work.
Yes, 6 N20s.
1860.
So you said 6 N20. What's the area?
1860.
Probably, but now you got to think of congestion. So this was 350, right? So I said before like 4 N24s, right? Spacing the bars about like 80 mil, which is okay. In your head you want greater than like 50 mil spacing. Once you add in like 6, stuff's getting cooked. Yeah. Because like basically you're thinking about like when they're pouring the concrete in to the formwork, there's like the largest rock is about 20 mil. So once you start reaching spacings that are close to that, there's like a possibility where the rocks get stuck between the bars. Yeah.
Do you have to go into this much detail, I suppose, by picking number of bars? Because in the question it just says minimum area.
Yeah, that's probably not needed for
So
this
if it's
specific
minimum
question.
Area, can you stop at that
Yeah.
1500 mil number you just calculated?
Yeah, you're probably right. I think you can end the question here, to be honest, if that's the wording of the question. But yeah. I guess for me, I'm just covering it because there might be a question which needs you to select the bars. So in your exam, that's very likely. It's very possible that the wording makes you select the bars. So it's good to go through the process, I guess. Yeah, question.
Is there like a minimum spacing requirement? Like let's say
Yeah.
you're at 6 and 20. How do you know if it's like going to satisfy?
Yeah, good question. I've got it. We finished the question, by the way. That was the last part. So in my notes, right? You'll find it. Oh, that's the table I was talking about. Yeah. So detail checks, clear spacing check. Oops. This is in my week. What is this? Week 6 notes, I think. On page somewhere like 2/3 down. I don't know, but yeah. Look at the Signal lecture notes. They'll be useful. Basically, clear spacing, that's the amount of clear spacing. You're just saying like, okay, what's the total width? Subtract the cover, subtract the stirrup diameter, and then subtract the bar diameter, and then it's like, okay, that's the clear spacing. And like there's like n, because when you have like multiple bars, you just divide it. You know what I mean? So that's just like a formula to be able to find that. Clear spacing must pass 4 checks, right? Greater than 25 mil is the American code, ACI. That's just what the American, it's just like a sanity check. But you're basically never gonna get this scenario and not this scenario, because we always assume that the course aggregate is 20 mil. So 20 mil times 1.33 times 20 mil is 26.6 already. So that's always gonna be greater than 25. The bar diameter, so if you're using your 28s, then you want to have a spacing greater than 28. If you're using 32, even more so. And then less than 300. But generally, it's just congestion-wise, if you look at it, because 50, like, I just keep my spacing greater than 50 mil. Because if you think about 50 mil, it's 5 centimeters. Any closer, and your bars are going to be really hard to build on the side, basically. Yeah. Make sense? Yeah, sorry, it's already 8 and I've only done one question, but I did it pretty slowly, so hopefully, I say slowly, but like there's probably bits that you guys might not be super comfortable with anyway. Do you guys have questions or no?
I've got one.
Yeah, man.
How lenient are they with partial marks? Like, let's say you fuck up.
I like the questions you're asking. Yeah, okay.
Let's say you fuck up the load combos at the very beginning of the question.
Oh, and like carry on error.
Yeah.
I don't know. I don't know is the answer.
Surely they're not going to mark the whole question down.
It depends on your marker. Depends on how they're feeling that day. I don't know. Like it really depends. I don't know how to answer that. Just do your best and pray, I guess. Yeah, you're welcome. No, okay, but if I'm okay, because like I'm conscious of time, I can run through concepts, but I might not run through another full question just because that took so long. But I just want to say like this is the hardest topic, right? So once you get this, it only gets easier. Okay, trust me. So the other topics, they're hard theoretically to understand, but the formulas are not too bad if you have a good set of notes. You can use my notes if you want, but like if you have a good set of notes, you can figure it out. You can figure out how to do questions. This is the hardest topic. Columns is just this and then extra, right?
What is the nature of the questions in the first 20%? You say something similar.
Yeah.
What are the questions like?
Basically, if you look through the workshops, the first 3, I think, are the ones which are more like material science. That is the nature of them. They're pretty much all that workshop style question. Yeah.
Okay.
So like moisture content, that kind of stuff. You can remember it. Yeah.
Not too bad.
It's okay. I don't want to like comment on it because don't want to give you guys point you guys in the wrong direction.
What was it like? What's
It was pretty much like the workshop questions, but variations of them. So if you, yeah. Yeah. If you look at the past papers, just have a look at those, and you kind of get an understanding. It's like the past papers are kind of doing like what the workshops are doing. So I'm just going to practice the workshops.
Yeah, I can't agree with that.
Yeah.
I'd like to say something. So I wanted the last lecture, the very last lecture, and this Professor Kim said that it's either the last question will be either serviceability or the interaction diagram. So it's one of the two.
That
The rest are like Shear or the Flexural is like pretty much guaranteed.
Oh, so he told you, pretty much. No, okay, so you can narrow it down a bit more then.
It's in the recording, like it's in the.
Yeah. Okay. So pretty much, right? There's 4 topics. So he's saying practice flexure, practice shear, and it's 50-50 between columns and serviceability.
Yeah, and the interaction diagram.
That is part of columns. Yeah. I will explain them all very quickly.
Those questions in the workshop today, it took like an hour and 40 minutes to go through the interaction diagram.
Yeah, because it's ridiculous.
That's right. It was a 2-hour exam. It was like an hour and 40 minutes to go through.
Okay, I'll go through. Okay, I'll go through all the topics very quickly. Okay, so that was flexure. I just covered flexure pretty briefly, right? Let's go through shear. Okay. All right. Just we just got a little bit longer, guys. Let's keep on. So shear, right? The first thing you need to know about shear is shear force diagram, right? So we're basically comparing that to be less than VU, I think it's called. But it's like it's a beam check as well. So you're kind of carrying through the same logic at the start. Like, so you know how you solve for shear force diagram and then you find the bending moment diagram? Now for shear questions, we kind of just don't need to do the bending moment part. We just go up to the shear part. But there's one hard kind of part about it in terms of, well, there's two kind of bits which are a bit harder, I guess, about it. One is pattern loading. So let's just say, here's an example. This is WG, right? So that's just dead load. That's just like self-weight or something. It's just across the entire beam. And then we also have live load, right? I'm not going to put numbers to this. I'm just going to tell you intuitively, right? There's 3 scenarios of loading, right? So here's the first scenario. Okay. And this is more of a shear kind of, it's like something you'd find in a shear question more than a bending moment diagram question, the pattern loading concept. There it is. Sorry, they updated this app recently, so I'm not super familiar with some of the new features. So, scenario 1, live load across the entire beam. Scenario 2, live load on one half the beam. Scenario 3, live load on the other half the beam. So I'm just going to draw what the shear force looks like in all the scenarios, right? First one is what you'd expect. It looks like that, right? Second one, what's going to happen is it's going to look like, it's going to go down more on this side and less on this side. That, okay? And then vice versa. I'm kind of exaggerating the amount, but what you're going to find, I'm just going to put in random numbers, okay? This is going to be 100, this is going to be 100, this is going to be like 80, and then this is going to be like 20 or something, and this is going to be like 20, and this might be like, I'm just making this up, but this be like 60 or something, negative 60. It's going to look something like this, okay? So we take the worst case scenario in different locations for all 3. So basically, in the first scenario, you're going to have the worst at the supports, right? It's the most loading, if you think about it, right? Because we've omitted the loading from this part of the beam, right? We're not increasing the loading, we're just omitting it from part of the beam. What this doesn't capture is the fact that in the middle of the beam, there might not necessarily be zero shear. So if we pattern load it, we're going to get something more like this for the middle, right? So the shear force envelope looks like this, right? Because this is going to be the worst case scenario from the first case. And now we're going to chuck in the worst case scenarios in the middle for the other two cases, right? Got it? So that's how a shear force envelope looks. Now the second part that's going to be hard about calculating the left-hand side for shear force is we're going to need to go away from the support. So the reason for this is because when you have a concrete beam, usually it's usually formed with concrete beam connected to concrete columns of walls, right? Oh, sorry. Let's just say concrete beam to concrete columns, right? It might be concrete slab to concrete walls, but same idea. Because basically, if we map the bending moment diagram, it's not really going to look like this because there's some rigidity. The bending moment is actually going to have a negative moment of supports like that, right? Similar idea for shear, right? So if I map a... Sorry. I'm just going to... Umbrella. So if I map the shear, right, of this beam, like this, right? The idea is that even though the max shear is actually at the support, what happens is there's a rigidity to this column to beam connection, and we have to, the code tells us to go a little bit away from it, and by a distance of DO. So DO is depth from compressive fiber to compressive side, let's just say, to outermost tensile steel. So this is a cross-sectional dimension, right? It's like if there's two layers, it's like to here, the outermost, right? So what's going to be strange is that this is in millimeters, right? But when we take it for a shear force, it's going to need to be converted into meters, so keep that in mind, right? And then basically you take whatever number this is, right? Let's say 100. Find that slope, right? Minus slope times that distance, dO, right? And that's going to be your shear force, design shear force, I think that's usually called. Right? Makes sense? You guys know how to find that slope, right? Rise and run? Okay, good. I've said it probably like 100 times today. Yeah. So that's how you find left-hand side. That's the confusing part. The rest of the steps you can probably follow, but I'll just give you a very, sorry, I know I say brief, but then I like talk for like 20 minutes. But the idea is if you have a concrete beam, right? You have the, we can like pretend it's a truss, pretty much. You guys have seen trusses, right? So we have our top and bottom Rio, right? That forms the top and bottom chord of our truss, okay? And then we're also gonna have, yeah, let's just draw a truss inside this, right? It'd look maybe something like that or something, whatever. Okay, let's just pretend I drew like an even amount. The idea is that these diagonals are called compressive struts, compressive concrete struts, right? And then you're gonna have your Rio tires, right? So the idea is that basically it's really hard to predict how concrete is gonna resist and shear, right? So I guess that's just like a pretty general definition, right? But we can think of concrete being able to resist shear at a certain angle, like most effectively, right? In the simplified method, this is 36 degrees, right? But then there's like a more complicated example in the code. But we're trying to match the concrete ties to be able to, I'm like trying to balance like saying this simply versus just going through the entire code. Basically, these ties have to match the concrete strut force, right? And these ties would be massive unless we space them to overlap. So say we move the ties closer, kind of more shown like this, right? That will resist more shear force, right? So if you have a smaller spacing between your shear ties, that's going to resist more shear force. If you have a larger spacing, it's going to resist less. But the idea is that in a concrete beam, okay, I'm kind of just yapping, but in a concrete beam, what you'll see is you'll have your top and bottom axial bars, which is what we designed from like the flexural design, okay? And then we're going to basically, okay, here's a shear force diagram, right? I'm just going to draw the simple one. Here, there's more shear force, so we're going to have closer spaced ties, right? Here, there's less shear force, so we're going to have further spaced ties. That's the idea. So the concrete and how much shear it can resist is constant throughout, right? But the ties is what we can change, right? That's the kind of like parameter that we're allowed to modify. So we need to compensate for the concrete's lack of ability to resist shear by adding more ties where there's more shear force. That's the bottom line. That's what all the calculations in the code go through, essentially. So they're really like, it's going to do your head in because the theory is like kind of cooked for this topic. But if you follow the steps, it's actually very straightforward. It's very like step by step. Yeah, that's shear. Do we have time for more? I don't know. What do you guys feel like? Yes or no? I'm kind of getting a no vibe. I might just say one more thing about serviceability. But yeah, okay, let's just talk about serviceability for a sec, right? So, you know how before we were talking about these being the combinations for load combos? That only applies to strength, right? Keep that in mind, right? Because when you do service, short-term service loads is G plus that, phi S Q, and then long-term loads is like that, right? Short-term is 0.7, long-term is 0.4. Let me just explain this with like kind of like a metaphor. So basically service loads are everyday loads, right? So we don't need to exaggerate anything. In fact, we under-exaggerate some of them because in any given day, right, how full is this classroom going to be, for example? It's probably not going to be to its design limit, right? Like here, we might be occupying like 40% of what the live load capability is for this room, right? So in the long run, it'll average out to be less, right? In the long run, like tomorrow it might be empty because it's a Saturday. On like a exam day or something, and say they set up exam tables in this room, it might be at full capacity or even higher, right? So we average it out to say long term, 40% of the live loads over the entire lifespan. In the short term, we're saying like, okay, like say it's a busy exam period. In the short term, like that busy exam period week, see man, it might be at like 70% capacity between like day and night time, right? That's how you can kind of think of these load combos. So when doing service questions, don't use those strength combos. Use the service loads. There's probably not much else to talk about without just going super in depth. Maybe I'll talk about interaction diagram quickly. So it looks like this for concrete, right? Something like that. So that's axial strength. This is moment, right? So this is what you were talking about in terms of Taewon might ask something about this.
I know the exact question. No, I don't know the exact question, but I know the structure of the question he
Yeah.
asked.
There's like 5 different points, right?
Yeah, I should do.
Yep. There's like the tension point, pure compression point,
I think it's
Yeah.
given, he doesn't really try to hide anything.
Oh, okay.
Like like
Probably
you
do
could-
columns. Yeah.
you could kind of guess what's the 40 marks gonna be.
That's crazy.
Um,
Oh no! But he says service or interaction, right?
Service all interaction for the last question.
So question 1 will be will be flexure. Question 2 will be shear, and then question 3 it sounds like is ambiguous on it.
Yeah.
So practice about it,
He
basically.
literally says service or interaction either.
But those are 2 different topics.
I know.
So it's like one or the other.
Either.
Yeah. No, that's good to know though. So you will have to study shear. Anyway, there's like all this interaction stuff. Just keep in mind the idea is that if you don't have any squashing on concrete, right, and you put it into bending that way, it's gonna be pretty weak because it's gonna reach its tensile failure point at the same rate as a beam, right? But if you squash it a little bit, it's actually gonna be stronger, right? Just imagine I had a stack of books, right? And that's like our analogy for concrete, and I'm squashing it together. It can actually bend better because I'm squashing it, right? So like in like, it can be like lifted off the ground if I squash it. Does that make sense? That's what happens with concrete, and that's actually the kind of like fundamental principle behind pre-stress concrete, if you've heard of that before. There's also like a topic on a UNSW. But yeah, it's really cool. So yeah, basically if you squash concrete a bit and bend it, it's actually be stronger in bending. Yeah. Okay. Class dismissed. Oh yeah, thanks.